Hey there, curious minds. Have you ever wondered why quantum measurements always give definite results, even though quantum systems are in superpositions of many states? Alright, so first let's cover the basics. In quantum mechanics, we have this thing called the wave function. The wave function evolves deterministically according to the Schrödinger equation. Now, this means it can be a linear superposition of different states. Picture it as a blend of all possible states a system can be in. But here's the kicker. When we actually measure the system, we always find it in one definite state. How does a superposition of many possible states just collapse into one single outcome? That's the essence of the measurement problem. According to the Schrödinger equation, the wave function evolves over time in a smooth, predictable way. But when you measure it, something weird happens. The act of measurement seems to force the wave function to collapse into one of the possible states. This collapse isn't predicted by the Schrödinger equation, which only describes the evolution of the wave function, not its collapse. So, why can't we predict the exact outcome of a measurement? Why do we only get probabilities? This is where things get really interesting. If we consider observers and measuring devices themselves as described by quantum mechanics, they should evolve in a deterministic way too. But we still can't predict precise results, only probabilities. Why is there this disconnect between quantum reality and the classical reality we observe? Many interpretations try to tackle this issue. The Copenhagen interpretation, for instance, suggests that the act of measurement causes the collapse. Meanwhile, the many worlds interpretation proposes that all possible outcomes happen, but in different branching universes. This puzzle still keeps physicists up at night, and who knows, maybe one of you watching this will crack the code someday. Imagine a sealed chamber containing a cat, a vial of poison, a radioactive atom, and a Geiger counter. This setup is connected such that if the Geiger counter detects radiation from the decaying atom, it breaks the vial, releases the poison, and the cat dies. If no radiation is detected, the cat remains alive. Here's the mind-bending part. According to quantum mechanics, until we open the chamber and observe the system, the atom exists in a superposition of decayed and undecayed states. Consequently, the cat is simultaneously alive and dead, existing in a superposition of both states. This scenario is famously known as Schrödinger's cat. When we finally open the chamber to observe the cat, we see it either alive or dead, not both. So, how does the indefinite superposition of states collapse into one definite outcome? When exactly does the measurement occur? Is it when we open the chamber and observe the cat? Or does the measurement happen earlier, perhaps when the Geiger counter detects the radiation? And what defines the measurement apparatus? Is it the Geiger counter, the poison mechanism, the cat, or the chamber itself? The Copenhagen interpretation is the oldest and perhaps the most widely accepted view of quantum mechanics. Coined by Niels Bohr and Werner Heisenberg, it posits that the act of observation causes the wave function to collapse, turning a quantum superposition into a single definite state. This idea is often summarized by the phrase, "shut up and calculate," emphasizing practical computation over philosophical pondering. However, not everyone agrees with this view. Hugh Everett's many worlds interpretations suggests that all possible outcomes of quantum measurements actually occur, each in its own separate universe. According to this view, there is no wave function collapse. Instead, the universe continually splits into a multitude of parallel realities. Another fascinating approach is the de Broglie-Bohm theory, which introduces additional data to describe the system, including the precise positions of particles. This theory suggests that what we perceive as wave function collapse is merely an interaction with the environment separating wave packets in configuration space. Objective collapse models offer yet another perspective. These models propose that the Schrödinger equation has non-linear terms that cause the wave function to collapse spontaneously. This collapse is thought to be triggered by some unknown external field, potentially gravitational in nature. But there's another crucial concept we need to discuss: quantum decoherence. The phenomenon of quantum decoherence, firmly established in the 1980s by researchers like Eric Jüss and Heinz-Dieter Zär, offers a compelling resolution to the measurement problem. Decoherence suggests that the environment itself causes the classical appearance of macroscopic objects. Essentially, it explains how the fuzzy boundary between the quantum micro-world and the classical world comes into focus. Zay and other proponents argue that decoherence doesn't describe the actual collapse of the wave function. Instead, it explains the conversion of quantum probabilities, which exhibit interference effects, into ordinary classical probabilities. This process helps to clarify why we don't see quantum superpositions in our everyday lives. Quantum decoherence has even become an important part of some modern updates to the Copenhagen interpretation, particularly those based on consistent histories. However, it's important to note that while decoherence helps explain the transition from quantum to classical, it doesn't fully solve the measurement problem. It doesn't tell us why a particular outcome is observed. It merely explains why we don't see superpositions at the macroscopic level. As noted by Schlosshauer in a 2006 article, several proposals have been put forward to elucidate the meaning of probabilities and arrive at the Born rule. Yet, no decisive conclusion has been reached regarding the success of these derivations.